Okay, so hopefully you had some success drawing the electron configuration for some of these. The SbCl5 one is pretty straightforward. S, B, 5 chlorines, 1, 2, 3, 4, 5. We add up the number of electrons. Now it's always important to find the number of valence electrons to know if you need to consolidate electron density or extra lone pairs need to show up somewhere on the central atom. So adding these all together, we have 7 times 5, 35, plus an additional 5 for the antimony. So that's 40. And again, we knew that because of the periodic table, right? We can see antimony is, whoops, what have I done here? There we go. You can see the antimony is in row 5 here, right? So 5 electrons, chlorine brought in 7 each. So that's 35 electrons, and when we put 1, 2, 3, 4, 5, 6, we didn't need to put more electron density here because it already has access to 8. But if we put 6 electrons on all 5 of these, that's going to be an additional, well, let's see. We said we had 40 electrons total, 7 times 5 plus the 5. So there's now 8 electrons around each of these, 8 times 1, 2, 3, 4, 5, so that's 40 electrons. So that compound looks good. Antimony brought 5, has access to 1, 2, 3, 4, 5, so there's no valence charge, or no formal charge on any of these atoms. Okay? Now, if we look at HCO3 minus, try to draw that structure, central atom with oxygens. And what did we say about the hydrogen, Samantha? Were you there for that? What did we say about the hydrogen? Where does the hydrogen go?
It's attached to one of the oxygens.
That's right. It's attached to one of the oxygens. Very good. And so this being an ion for an oxyacid, right? The acid is coming off of the oxygen in oxyacids. All right. Number of electrons. Taewon, did you get to count up how many electrons were in this molecule? How many valence electrons should be used?
24.
24. All right, 24 valence electrons. Okay, and those 24 valence electrons, we have 2, 4, 6, 8 already on there, right? All right, now we need to get 16 more valence electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I guess we needed some here, 13, 14, 15, 16. All right, I should have started with the central atom because it didn't have 8 to start with. But I can see that when I have it distributed like this, there's some problems with this compound, right? Oxygen doesn't have enough electron density available to it, right? So I can't form a double bond here with those electrons, all right? I could remove these and form that double bond like that. Let's see. I guess I could do that. All right, Emily, tell me, is there anything wrong with this structure that I've drawn?
Is the oxygen at the oxygen at the top with the hydrogen? It has just 5 right around it.
Okay, it has a formal charge then of what? 6 is how many it brought, minus 5. It has a formal charge of plus 1. Right? Any other problems with any of the other oxygens or the carbon?
The other oxygens all have 7.
So what would its formal charge be?
Negative
-1. Very good. -1 for these oxygens. So that's an indication that what, Samantha? Or sorry, Harry, what is that an indication of?
That it hasn't. There's a better way of doing it to balance it.
Yeah, that's not probably not a correct structure. Okay, so 1, 2, 3, 4, 5, 6. 1, 2, 1, 2, 3, 4, 5, 6. So if we want to rearrange electron density, what might we do, James Oliver?
We had like double bonds for the oxygen atoms that aren't attached to the hydrogen.
So move this double bond over to here. Is that what you're saying?
No, get the 2 electrons from both of the other oxygens and make a bond with that.
Oh, like this?
Yeah.
Okay. Are there any problems with that structure? James Willis?
Carbon has too high of an electron density.
Yeah, too many electrons available to carbon. Carbon can't have an expanded octet. Right now it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 electrons. How do we know that carbon can't have an expanded octet?
It doesn't have a D block.
Yeah, it's only in the second row or lower. It's not lower than that. It's only the second row. So it needs to be in the third or lower to be able to have an expanded octet. So that's not going to work out for us. Also, we still had our -1 formal charge, sorry, +1 formal charge there. So let's see. Catherine, can you think of something else we can do?
Not sure.
Well, what if we so here, when we had this structure here, we had a -1 charge here, and our formal charge, -1 formal charge there, and a +1 formal charge there. So what this is kind of directing us is, like we saw, we'd like to make these double bonds to get rid of that formal charge, but we'd also like to get more electron density here. So maybe we bring more electron density there by bringing this double bond out here to form lone pairs, non-bonding lone pairs. And then we bring just one of these in like that. Right? Now, let's see, whose is it? Katie, what's the formal charge on this oxygen right here, Katie?
It's 0.
It's 0. Very good. And the formal charge here, Katie?
It's also 0.
It's also 0. And this one, Katie? Any ideas? What's the formal charge there?
That one is still -1? Or
That's right.
plus?
That's right. Still -1. It brings 6 electrons. Subtract how many it has right around it? 7. So it's a formal charge of -1. Now, is it okay for this compound to end with a formal charge? Landon?
No.
Well, actually, because it's HCO3 minus, it's going to have to end up with a formal charge. All right, so that negative sign is meaning that somewhere on here there is a negative charge, and now the Lewis dot structure tells us where it's at. That's also consistent with our understanding of if I take this compound, HCO3 minus, add a proton and form H2CO3, right? Now we have a general understanding that this thing, move this out of the way, combines with a hydrogen ion, and these electrons come up here and result in a bond there. Okay. Very good. So let's try that again. This time we're going to draw, I'm going to break you guys up into groups, and we're going to try to draw the Lewis dot structure for this acid, H3, well actually this acid, or this compound, this polyatomic ion, H2PO4 minus, H2PO4 minus. So I'm going to break you up into groups, and I want everybody to work on this H2PO4 minus. Okay. And dihydrogen phosphate ion, which is the ion of an oxyacid, phosphoric acid. Okay. So I think that most of you did, or almost all of you, if not all of you, did a very good job of recognizing that the hydrogens are going to come off of the oxygens. You can't hear me? Let me see here. Okay, we okay now? All right. So, most of you did a really good job of recognizing that the hydrogens need to come off the oxygens, right? There's a couple reasons. One major reason that we are going to remember that is we have to recognize that this is the an ion from an oxyacid, an ion from an oxyacid. So the hydrogens are going to be coming off of the oxygens. Okay, hydrogens like to be around oxygen. Elements or compounds like this, where you see 4 oxygens and a phosphorus and then 2 more, right? Having 6 ligands isn't impossible, but generally unlikely for smaller elements like between carbon, or definitely unlikely or impossible for carbon, nitrogen, oxygen, and fluorine, right? Because of the location on the periodic table, but generally unlikely for these smaller elements up here. All right, so we have this skeleton structure. We counted up the electrons. Let's see. Catherine, do you remember how many electrons you guys had in this party?
Math.
Let's see.
32?
32. Very good. 32 valence electrons and 6 for each oxygen, a 5 for the phosphorus, 1 for each hydrogen, right? And then 1 for that electron there. You always have to remember, and if you ever end up with an odd number, it's generally because you didn't count these electrons. Not always, but you always have to pay attention. The odd number will help you sometimes. Sometimes that'll be a -2, so it won't help you. But remember, the electrons, or the charge means that there's an extra electron. All right, so as we begin to distribute electron density, first we would go to the central atom, but it looks like we have plenty of electrons available to us. We could start 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. All right, so we have 32 valence electrons on our compound now. So all the electron density is distributed. Now, the question is, can we improve the compound? Everybody has 8 electrons available to them, or hydrogen has 2. But can we improve the compound? Katie Thomas, what do you think?
Yes.
How?
Take 2 lower oxygens and form double bonds to the phosphorus because they have too many electrons.
All right. So we see that our formal charges on these oxygens are -1. What's the formal charge on the phosphorus right now, Katie?
Is it -1?
Let's count it again. What is it? It brought 5 electrons, right? Minus,
Or just a 1?
yeah, just a positive one. So those positive signs, those negative signs, those are telling us where electron density is more of and where it's missing some, right? Okay, so we're going to draw a new and improved, right? Phosphorus with some, we're going to bring in some electron density here. Okay. Should I bring in some more electron density from here, Landon?
No.
Why not? It would look so cool, wouldn't it?
Yeah, but it wouldn't come out as the original formula was planned, having the minus charge.
Okay, so if I did bring electron density in there and formed this,
Hello.
yes. If I did do that, then what would that mean? Where would my formal charge be now, my negative formal charge? Or did I get rid of my negative formal charge altogether? What do you think, Nikki?
Your formal charge would be -1 on the phosphorus, wouldn't it?
Right, I'd have the -1 on the phosphorus.
Is that
So-
okay or no?
Yeah, that's the question now. Phosphorus. Which of these two, negative charge on the oxygen or negative charge on the phosphorus, right? Which of these two is better for us? Anybody have any explanation for why one might be better than the other, or are they both feasible? Anybody can comment on that.
The phosphorus, doesn't it follow the expanded octet rule?
It does. It can have an expanded octet. And so that's okay. It's okay if it has this many electrons. We should have mentioned that when we brought those electrons in here. The reason why we could bring those electrons in is because phosphorus can have more than 8 electrons available to it. But now in this scenario, where should our formal charge be? Which is better, right or left? Should the formal charge be on the oxygen, or should it be on the phosphorus in the middle, or does it not matter? And what is our argument for that? What do you think, Precious?
Sorry, I really don't know.
Okay, Samantha?
Would it be on the phosphorus because it can have that extended octet?
Well, who would be stabilized by that extra electron density more, the oxygen or the phosphorus?
The oxygen.
How do you know that? That's our periodic table, right? Oxygen is more electronegative than phosphorus, so oxygen is going to be stabilize the situation more if it has more electronegativity. So that's an indication that this one is the one that's going to be correct and not that one. Also, another way we could remember that is when this is added to H+, right? The H+ attaches to that oxygen. These electrons come over here, grab onto that hydrogen, and the result is phosphorus, oxygen, hydrogen, phosphorus, oxygen, hydrogen, phosphorus, oxygen, hydrogen. Right? 3 oxygens with hydrogens. Okay, very good. Now, with our remaining time, we want to have a quick conversation about the length of bonds and the strength of bonds. Okay, let me bring up this slide here. This one here. Look at it a little bit. It shouldn't be surprising to us that a double bond is stronger than a single bond, or it's harder to break. A double bond requires 615 kilojoules to break a mole of them, as opposed to a single bond requiring 348 kilojoules to make a mole of those bonds. All right? And a triple bond requires even more energy to break. And, you know, we already talked about this. We've seen this before, that, you know, if you have X and Y and you form a bond, right, that has to release energy, right? That process releases energy because we're forming a bond. Therefore, to break it, the delta H has to be a positive value, has to require energy to break it, right? So that's, you know, consistent with this. A single bond, there's some energy, but you add another bond, and now there's more energy required to break that bond, okay? So, with that information, what do you think, Taewon, which one of these bonds is harder to break? The oxygen-phosphorus single bond or the oxygen-phosphorus double bond? What do you think, Taewon?
I'm not sure.
Okay. Any ideas, Emily?
Wouldn't the oxygen with the double bond be stronger?
Yeah, that's right. This one is stronger. It's harder to break. There's more bonding occurring, so it's harder to pull those apart. Now, I didn't mention anything about the distance, but you can see here a carbon-carbon bond is 154 picometers. Carbon-carbon double bond, 134. Carbon-carbon triple bond, 120. So with that in mind, what do you think, Harry? What would be shorter? An oxygen-phosphorus double bond or an oxygen-phosphorus single bond? Which one would be shorter?
The double bond.
Yeah, the double bond is shorter. So there is a difference between these oxygen-phosphorus bonds on this molecule as we've drawn it. However, when you perform experiments to measure the strength of these bonds or the length of the bonds, what we find is that the bonds are not the length of single phosphorus-oxygen bonds, and they're not the length of oxygen-phosphorus double bonds either, but what they are is they're a length of the average. So if you took the length of 3 single bonds and 1 double bond, added them together, divided it by 4, you would find that's the length of these oxygen-phosphorus bonds. Also, the strength of these oxygen-phosphorus bonds are an average of the strength of these 3 single bonds and that 4th bond averaged together. Okay? So, again, what that tells us is that this structure that we've drawn is not only is this double bond here, but it takes turns rotating around the molecule. So sometimes this electron density hops onto the phosphorus and then goes onto there. The electron density comes off of that hydrogen, and a hydrogen from somewhere else forms a bond here, with electron density, let's see, 1, 2, 3, 4, yeah. Oh, 5, 6, there we go. So those electrons there go and get that hydrogen there. So that double bond takes turns being in different locations. And so you have the double bond here, the double bond here, we could have the double bond over here. Whoops, we're supposed to be drawing one of these as a negative charge, right? So the double bond there, then we'll have this one as a negative charge. All right, and you can see that there's a couple other scenarios where the oxygen, so there's 1, 2, 3, there's just one more, I'll draw it then. Right? So all of these are actually occurring all at the same time. And it's not just this, it's all of these. And we call these all resonance structures. Resonance structures. It's the movement of electron density on a single molecule. Okay? And so what that does is it makes it so that the length of these bonds are an average of all of the lengths, and the strength of those bonds are also an average of all of those strengths. Okay, and just one more thing here. We'll show a picture of all the different resonance structures for the NO3 minus, for example, right? The double bond can be here, here, or here. And if I were to ask what's the bond length or the bond strength of these, you would have to look at the average bond length and the average bond strength for all those. All right. Well, that's it for Chapter 9. We're going to have class on Friday, and Chapter 10 really just adds a couple more ideas to this, and we're not going to get all of them in, but we'll be able to get some of them in. So we will meet on Friday, Chapter 10. That's our last class. We'll just build on our knowledge here a little bit. And then we're going to take the final. The final will be around the 15th. Hopefully I can get it open the 15th, but if not, it'll be open the 16th, and I'm not sure exactly how long they'll let me open it. I think I can keep it open until the 20th, but if not, it'll be open the 16th, 17th, and 18th. If I can keep it open to the 20th, I will, but it'll probably be better if we take it by the 18th so that we have plenty of time to go over any issues as far as grades go. We're going to be using Proctorio, all right, Proctorio. So Proctorio, I haven't used it myself. Why don't you guys tell me in the chat window if you've used Proctorio with a yes or no? Okay, so many of you have. For those of you who have or have not, or you want to become familiar with it, I have a practice quiz open for us. It's called Practice with Proctorio. It's the same quiz as the chapters 1 through 8. All right. It's just kind of to give you an opportunity to become familiar with the Proctorio component and make sure there's no issues. I think it is browser specific sometimes, so you'll have to follow the rules and figure out what you need to do to be set up for it. Again, this is just a practice. It wouldn't let me make a practice without having some points associated with it. So there are some points associated with this, but as soon as we're done practicing with it, I'll delete it so it won't show up in your grade anymore or ever. Okay. Other than that, I think that'll put us on the right path to be prepared to perform well on the final. Are there any questions? If not, see you later. If you want to hang out and ask a question in private, that's fine too. Remember to work on your lab. If you have any questions about lab, we've had lots of videos of people asking questions and being helped. You can ask a question and be helped too, or you can follow the lab or the videos up there as well. All right, see you later.